Greetings of the day. In our last lecture, we developed mathematical equations for computing the susceptances of compensators for compensating the three-phase load for unbalance and for reactive power compensation, that's power factor correction. The approach was very simple. First of all, we considered a delta connected load, and it was an unbalanced load. The idea was to connect the compensator to this load for compensation purposes. What we did, we used the symmetrical components, zero sequence component of current, positive sequence component of current, and negative sequence component of current were computed in terms of the line currents. And line currents in turn were calculated or computed in terms of phase currents, that is in terms of the load admittances. Then we got mathematical expressions for positive sequence component of current drawn by the load and negative sequence component of the current drawn by the load. Then what we did, we connected compensator in parallel with each branch of the load, assuming that compensator susceptances are B gamma AB, B gamma BC, and B gamma CA. Then we defined the two objectives of compensator, shunt compensator. First objective was to balance the load. That means whatever is the negative sequence component of current required by the load, that should be supplied by the compensator, and hence that will result in balancing of load and hence balanced line currents. Second objective was set for power factor correction. Beta was defined as a parameter, and beta equal to tan phi, that was assuming a value of phi. For example, phi cos phi, that's power factor, you could take as 0.9, 0.95, or even unity power factor. For unity power factor, beta would be 0. And then once we defined these two objectives, we developed put these conditions into the original equations, and then after certain mathematical manipulations, we got equations for compensator susceptances B gamma AB, B gamma BC, and B gamma CA, but in terms of sequence component of currents I1, IL1, and IL2. Then we transformed, or we changed the equations, deriving the mathematical expressions for compensator susceptances in terms of actual load currents. Okay, if you remember, these were the mathematical expressions that we finally got for load balancing and for unity power factor operation. The three equations were B gamma AB equal to -1 by 3V times imaginary part of load current or line current IAL plus imaginary part of A times line current IBL or load current IBL minus imaginary part of A square line current or load current ICL. This was B gamma AB. B gamma BC was got as -1 by 3V, where V is the source voltage, assuming source to be balanced, -1 by 3V times minus imaginary part of IAL plus imaginary part of AIBL plus imaginary part of A square ICL. Okay, and third susceptance of third branch B gamma CA was calculated to be, we derived it as -1 by 3V times imaginary part of IAL minus imaginary part of AIBL plus imaginary part of A square ICL. This is what we got finally. All the compensator susceptances for load balancing purpose and for power factor correction to unity, we got in terms of line currents or load currents IAL, IBL, and ICL. Now, what we can do, we can use some methods, two methods. One method is called sampling method and another method is called averaging method, to convert these equations into their time equivalents. I mean, they are not in terms of their time, they are not time equations. We have an RMS value of load current or line current IAL, similarly IBL, ICL, multiplied by these operators A square, and then you have to take imaginary part. It is still a bit difficult to find these load currents, multiply them by these operators A and A square, and finding their imaginary components. To actually implement the algorithm and calculate these compensator susceptances B gamma AB, B gamma BC, and B gamma CA, we will use control algorithms. Two control algorithms will be there. The first one that we are going to discuss is called sampling method. It's called sampling method. Why it is called sampling method, you will come to know in a minute's time. Okay. Now in this sampling method, let us consider in these equations you have the line currents IAL, IBL, and ICL. For example, if you again write this B gamma AB, it is minus 1 by 3V times imaginary part of line or load current IAL plus imaginary part of load current or line current A times IBL minus imaginary part of line current or load current A square ICL. So we can now take these currents IAL, IBL, and ICL and represent them in terms of in time domain. Now, as far as this line current IAL is concerned, the load current or line current IAL is concerned, it has a real part and it has imaginary part. So it has a real part and it has J imaginary part. So the real part can be written as IAL R means resistive, which means real part, plus imaginary part can be written as JIAL X. X means reactive part or imaginary part. Now instantaneous, let us represent this or denote or write this equation for line current IA in terms of time, that is instantaneous phase A current. I will write instantaneous phase A current. It is written as you know, small ial, because instantaneous values are represented, denoted by small letters and RMS value by capital letters. So IALT, instantaneous value, it's a function of t, is equal to root 2 times RMS value, but imaginary quantity of IAL e raised power j omega t. You go back to basic electrical engineering when you were introduced phasors, and when your equation for voltage was considered sinusoidal. You wrote that V equal to Vm sine omega t. Your teacher must have told you that it is imaginary part of Vm e raised power j omega t. That is imaginary part of what is Vm? Vm is peak value, which is equal to root 2 into V. Okay, and what is this e raised power j omega t? It is cos omega t plus j sine omega t. From the phasor algebra, since it has to be sine omega t, that is the imaginary part. So that's why we take imaginary part. So finally it becomes root 2v. This is the real part. Real part you have to ignore because you are taking imaginary part. Imaginary part is sine omega t. What is root 2 into v? Root 2 into v is peak value. That's Vm sine omega t. So therefore V equal to Vm sine omega t is basically imaginary part of Vm e raised power j omega t, and we have proved that it is equal to Vm sine omega t. In a similar way, what we are doing, we have to write expression for instantaneous phase A current. That is root 2 into RMS value of phase A current. Root 2 into RMS value is peak value. Then imaginary part of e raised power j omega t. So that is equal to root 2 into imaginary part of, what is this IAL? It has a real part and it has a reactive part. I will write IALR, which is the real part, plus J I A, this is A, J IALX, which is the reactive part, e raised power j omega t. Okay. So IALT, that is instantaneous value of phase A current, is root 2 IM. IM means imaginary part. IM does not mean current, it is imaginary part. IAL R plus J IALX into what is e raised power j omega t? It is cos omega t plus j sine omega t. Okay, so that is equal to root 2 into imaginary part of, so IAR into cos omega t is IALR cos omega t plus j times IALR sine omega t plus j times IALX cos omega t plus j into j is j square is minus 1 IALX sine omega t. So simple, I am multiplying these two with these two terms with these two terms, and I get 1, 2, 3, 4 terms like this. So this is equal to root 2 into imaginary part of, let us take real parts separate. Let us split them into real and imaginary parts. We separate the real parts. First real part is ILR cos omega t, and second real part is this minus IALX sine omega t. Then we have imaginary part plus first j times first imaginary part is this IALR sine omega t plus then second imaginary part is this IALX cos omega t. That's it. Okay. Then what does this mean? If you take imaginary, you have to take only imaginary part. IM means imaginary part. So real part you don't have to take. So mathematical expression for instantaneous value of phase A current is equal to root 2 times imaginary part of this whole expression. So this is the real part. We will not write this. This is real part. The equation says we have to take imaginary part, and this is imaginary part. So it is root 2 times imaginary part. What is imaginary part? Your imaginary part is IALR sine omega t plus IALX cos omega t. Fine. This is the final mathematical expression for our IALT. Okay. Now we know that the three phase voltages are VA is equal to root 2V sine omega t. Phase voltage VB is root 2V sine of omega t minus 120 degrees, and phase voltage VC is root 2V sine of omega t plus 120 degrees. Okay. Now at omega t, I will write here at positive, I mean if you draw these three phase currents, phase voltages, this is VA, VB will start after 120 degrees somewhere here, this is VB, and VC will start further after 120 degrees, so this is VC. So this is the zero crossing of phase voltage VA. I will say at positive going zero crossing, ZC means zero crossing of phase voltage VA. This is phase voltage VA, and it's positive going zero cross. This is its zero crossing, it is positive going, because after this the voltage becomes positive. This is also zero crossing, but it is negative going zero crossing, because after this zero crossing the voltage acquires negative value. So this is positive going zero crossing. At positive going zero crossing of this voltage VA, what is omega t? Omega t is equal to 0 degree. Okay, so therefore when you put omega t equal to 0 in this equation, what will be sine omega t? What we are doing, we are sampling the current, instantaneous value of current IAL at positive going zero crossing of voltage. See, IAL, that is instantaneous value of phase A current, is because of this voltage VA. If voltage was not there, IA would not have been there. So we will try to sample this current IAL at positive going zero crossing of the voltage which actually caused this current. And which voltage is that? That is VA. So this is the positive going zero crossing of this voltage. At this instant of time, we will see, we will have a control algorithm, and we will have a zero crossing detector which will detect this zero crossing, and at this point itself it will take a sample of the current. So therefore at omega t equal to 0, which is positive going zero crossing of voltage VA, Omega t is 0, sine omega t is 0, and what is cos omega t? That is cos 0, that is 1. So therefore, the sample of current that we will get is root 2 times sine omega t is 0. What is cos omega t? Cos omega t is 1. So it is IAL. It is root 2 times IALX. And by the way, what is IALX? It is the imaginary part of the current. So we can say it is root 2 times imaginary part of the current IAL. So therefore, if you have to find the current IAL, if you have to find the current IAL, therefore current IAL, sorry, imaginary part of the current IAL, imaginary part of phase current IAL is equal to, that is instantaneous value of current जो हमने sample यहाँ लिया, by root 2. From this equation, what is imaginary part of IAL? IAL is the RMS value of this current. It is IAL by root 2. This is very important. For omega t equal to 0, that is for VA equal to 0 and dVA by dt greater than 0. VA equal to 0 means omega t equal to 0 is 0 crossing, positive going 0 crossing. And at positive going 0 crossing, VA is 0. And what is dVA by dt? The voltage is, it's the positive going 0 crossing, voltage will rise. So after this, voltage will go positive, and therefore the slope here is positive. dVA by dt is greater than 0. So what will you do? What will your control algorithm do? At this, first of all, you have to detect the positive going 0 crossing of this voltage VA. Suppose this is the positive going 0 crossing. Okay. At this point, your algorithm will read the instantaneous value of current, phase A current IAL. That may be here, that may be here. We don't know what is that instantaneous. That may be negative, that may be positive. Okay, we don't know. That depends upon the phase angle. And that is this. And divided by root 2, what will that give? That will give you imaginary part of IAL. The question is, why do we find this imaginary part of IAL? Because this imaginary part of IAL you will be using in this equation. Which equation? B gamma AB, compensator susceptance. Compensator susceptance is given by -1 by 3V times imaginary part of IAL plus imaginary part of AIBL minus imaginary part of A square ICL. ठीक है, तो इसमें आपको चाहिए था कंपनसेटर की ससेप्टेंस निकालने के लिए ब्रांच ए की AB की जो कंपनसेटर ससेप्टेंस है. फर्स्ट ऑफ ऑल यू रिक्वायर imaginary component of current, imaginary part of the RMS value of phase A current IAL, and we have found that. What is that? That's IAL T by root 2. But at what instant is it equal to IAL T by root 2? At positive going 0 crossing, where voltage VA is 0 and the rate of change of voltage or slope of the curve dVAT by dt is greater than 0. So therefore your control algorithm will read the instantaneous value of current at this point itself and divide that by root 2, and that will give imaginary part of IAL. This is how we find IAL. So this is calculated now. This is how your algorithm will calculate it. Okay. Now what you have to find? Second term you have to find. Second term is imaginary part of ABL. Okay. How to find that? For that purpose, we have to write a mathematical expression for instantaneous value of current IBL. First of all, I will write phase B current IBL. It is IBL, it has a real part plus JIBLX, and it has a reactive part, right? But I don't have IBL here, I have A times IBL. So if I multiply it by A, so I will get A times IBL equal to A times IBLR plus JIBLX. What is A? A is an operator, you already know, that is -1 by 2 plus J root 3 by 2 times IBLR real part plus imaginary part JIBLX. So A times IBL therefore is equal to minus 1 by 2 IBLR minus J1 by 2 IBLX, this into this plus this into this, then plus this into this, plus J root 3 by 2 IBLR, and then J into J is J square is minus 1 minus root 3 by 2 IBLX. Okay. Now let us separate real components and reactive components. The first real component is minus 1 by 2 IBLR. What is the second real component? This minus root 3 by 2 IBLX. And then imaginary components are J times first this root 3 by 2 IBLR, ये वाली term, and then minus 1 by 2 IBLX. ठीक है? So this is, therefore if you have to find imaginary part of this, for example here you have to find imaginary part of this. Imaginary part of this AIBL is equal to, this is real part cancel हम करेंगे, it is this root 3 by 2 IBLR minus 1 by 2 IBLX. But this is not what we want. We want imaginary, we want AIBL in terms of instantaneous value of the current. Okay, and this is not instantaneous value of current. This is the RMS value of real component of current, RMS value of reactive component of current, and it is very difficult to find real component of current and reactive component of current. What you have to do, phase voltage VB is this. It's positive going zero crossing is this. Let's call this positive going zero crossing X. This positive going zero crossing Y, or phase C voltage का positive going zero crossing, let's call that Z. So its phase B is positive going zero crossing is Y. At Y we will try to find what is the instantaneous value of phase B current. And then we will try to represent this imaginary part of ABL in terms of that instantaneous value. Let us see how we can do that. That is what we have to do. Let us see how we can do that. Now, instantaneous value, I will write here instantaneous mathematical expression for instantaneous value of phase B current. Phase B current. That can be written as IBL as a function of time. What is that equal to? That is equal to Im sine omega t, that is root 2 times this IBL RMS value, IBL e raised to power j omega t. तो यहाँ से आपको IBL मिल सकता है, imaginary part of IBL मिल सकता है, but I don't want imaginary part of IBL. What do I want? I want imaginary part of AIBL. So what I will do, I will modify this equation. I will write it root 2 into imaginary part of, I will multiply it by A because I need A here. A into IBL, okay, A into IBL e raised power j omega t. If I have multiplied it by A, I have to multiply it by A raised power minus 1 also. Because A into A raised power minus 1. What is A raised power minus 1? A raised power minus 1 is 1 by A. And what is A into A raised power minus 1? That is A into 1 by A. That is equal to 1. So A into A raised power minus 1, 1 barabar hai. So original form is retained. So if you have multiplied this expression by A to get this, you have to multiply this also by A raised power minus 1. And by the way, what is this A raised power minus 1? It is 1 by A. That is 1 by A is 1 at an angle of 120 degrees. That is 1. अगर ये angle ऊपर आप ले जाओगे, it will be at an angle of minus 120 degrees. तो इसका मतलब A का मतलब अगर है, A का मतलब है 1 at an angle of plus 120 degrees. A raised power 1 minus 1 का मतलब है 1 at an angle of minus 120 degrees. Remember it, it's very important. So, therefore, this is equal to root 2 into imaginary part of A. So, it is imaginary part of A. Okay, imaginary part of Wait for a moment. Yeah, A into IBL e raised power j omega t minus 120 degrees, क्योंकि अभी थोड़ी देर पहले हमें पता चला that a raised power minus 1 is nothing but 1 at an angle of minus a raised power minus 1 is equal to 1 at an angle of minus 120 degrees. तो यहाँ e raised power j omega t है और इसका एंगल है minus 120 degrees. So total angle will be j omega t minus 120 degrees. Right? Is that clear? So this can be now written as root 2 into imaginary part of, अब मैं a का वैल्यू लिखूंगा. What is a? A is minus 1 by 2 plus j root 3 by 2. Fine? And then I will split IBL into real component and reactive component. Its real part is IBLR plus reactive component is JIBLX into e raised power j omega t minus 120 degrees, which means cos of omega t minus 120 degrees plus j sine of omega t minus 120 degrees. Okay. A is this, IBL is IBLR plus JIBLX, and e raised power j omega t minus 120 degrees means cos omega t minus 120 degrees plus j sine omega t minus 120 degrees. Right? So let us further simplify it. So further simplification will give root 2. Okay. Now अब मुझे इसके imaginary parts खाली चाहिए. I will not write imaginary. I will find imaginary. See if minus 1 by 2 plus j root 3 by 2 is there. Okay. और यह सबसे पहले मैं what I will do, root 2 imaginary part of, let me write minus 1 by 2 IBLR minus j 1 by 2 IBLX, okay, plus j root 3 by 2 IBLR. J into j is j square, so that will become minus root 3 by 2 IBLX. Okay, so I have multiplied this with these two terms and this with these two terms. I got 4 terms. Whole multiplied by this thing, cos of omega t minus 120 degrees plus j sine of omega t minus 120 degrees. Right? अब इसमें मैं क्या करूँगा? I will take root 2 imaginary. First of all, I will write real parts. Real part is minus 1 by 2 IBL R. Okay. दूसरा real part है minus root 3 by 2 IBL X. Okay. Then I will write imaginary parts. Plus j times, what is my first imaginary part? Root 3 by 2 IBL R. And then minus 1 by 2 IBL X. This whole thing multiplied by cos of omega t minus 120 degrees plus j sine of omega t minus 120 degrees. Right? So this is the equation. अब इस equation में I will write IBLT, that is phase B current instantaneous value, equal to root 2. Now इस सब में मुझे imaginary part चाहिए, because as per this equation, what do I need? Imaginary part of this whole thing. See, if this first term is multiplied with cos of omega t minus 120 degree, it will become minus 1 by 2 IBLR minus root 3 by 2 IBLX into cos of omega t minus 120 degrees. So वो real term होगी, because this is real, this is also real. So therefore वो मैं लिखूंगा नहीं. Then if I multiply this term with the second term में j है, so it will become minus 1 by 2 j times minus 1 by 2 IBLR minus root 3 by 2 IBLX into sine of omega t minus 120 degrees. Since j is associated with it, तो ये इसकी imaginary term है. So since I have to write only imaginary terms, तो मेरी पहली imaginary term ये आएगी minus 1 by 2 IBLR minus root 3 by 2 IBLX into sine of omega t minus 120 degrees. ठीक है. उसके बाद मुझे then मेरी ये term है imaginary term. If I multiply this imaginary term with first cos omega t, इसमें j है तो ये भी मेरी imaginary term आएगी. So plus root 3 by 2 IBLR minus 1 by 2 IBLX into cos of omega t minus 120 degrees. That's it. इसकी दूसरी टर्म जो है this into this j into j is j square, वो रियल टर्म बनेगी, वो मैं नहीं लिखूंगा. So therefore my final expression for instantaneous value of phase B current is this. That is IBLT is equal to root 2 times minus 1 by 2 IBLR minus root 3 by 2 IBLX into sine of omega t minus 120 degrees plus root 3 by 2 IBLR minus 1 by 2 IBLX into cos of omega t minus 120 degrees. Now what should my control algorithm do? My control algorithm should now at positive zero crossing of phase B voltage, positive zero crossing of VB, that is point Y. Point X was positive zero crossing of phase A voltage VA. What is the positive zero crossing of VB? It is Y. तो यहाँ पे क्या ये करेगा? What it will do? Here omega, this is, see if this is omega t, what is this? This is omega t minus 120 degrees. So omega t minus 120 degrees is equal to 0. So therefore sine of omega t minus 120 degrees is sine 0. That is 0. And cos of omega t minus 120 degrees is equal to cos 0 degree, because omega t minus 120 degrees is 0, that is 1. So therefore इसमें sin, जब आप sin omega t minus 120 degree इस point पे लेके वो 0 होगा. So ये term गई. And you have cos of omega t minus 120 degrees, that is cos 0, that's 1. ये term retain हो जाएगी. So what is this? This is reactive component of current. So therefore you can write IBLT is equal to root 2 times and of course this is the imaginary part of the current, क्योंकि आपने imaginary लिया, root 2 times imaginary part of current AIBL. okay, क्योंकि थोड़ी देर पहले आपको याद होगा ये current IBL मुझे मिली, what was this? ये मैंने लिखा है AIBL. When we started deriving expression for IBL, we multiplied, we wrote IBL T as root 2 times imaginary part of IBL e raised power j omega t. फिर मैंने उसको क्या किया, मल्टीप्लाई किया a से और मल्टीप्लाई किया a raised power minus 1 से. So therefore this is imaginary part of AIBL. फिर मैंने जब इसको सॉल्व किया, I finally got this expression. इस एक्सप्रेशन में cos of omega t minus 120 degrees अब 0 हो जाएगा, ये टर्म 1 बनेगी, and you will get only this term. This term basically represents AIBL. So therefore IBT is equal to root 2 times imaginary AIBL. So that means IBL जो AIBL imaginary part of AIBL जो है, that is equal to IBLT by root 2. ये आपका IBLT है divided by root 2. Imaginary part of AIBL is IBL by root 2. Okay, so therefore we have proved that imaginary part of AIBL is root 2. Can't we similarly prove? Similarly, we can prove. We don't need to go for another derivation. We can write similarly imaginary part of A square IBL, A square ICL, that is equal to ICLT by root 2. So we can prove using the same analogy. See, imaginary part of A IBL is IBL by root 2, but at what? For VB is equal to 0, that is at positive 0 crossing of this voltage, and dVB by dt greater than 0 because slope is positive here. Similarly, imaginary part of A square ICL will be ICL by root 2 at VC equal to 0. That means at the 0 crossing of VC voltage, which is Z, and dVC by dt greater than 0. Therefore, our problem is solved. So therefore, we have three equations. Let me write. The first equation was B gamma AB is equal to minus 1 by 3V times imaginary part of IAL plus imaginary part of AIBL minus imaginary part of A square ICL. And my second susceptance of compensator was B gamma BC, that was equal to minus 1 by 3V times imaginary part of, well, of course, minus imaginary part of IAL plus imaginary part of AIBL, load current or line current IBL, plus imaginary part of A square ICL. And my third compensator susceptance B gamma CA was minus 1 by 3V times imaginary part of IAL minus imaginary part of AIBL plus imaginary part of A square ICL. Using sampling method, what we have done, using the control algorithm, what our control algorithm will do, it will find imaginary part of IAL at VA equal to 0. That means at point X, when VA is equal to 0, that's positive 0 growing, positive going 0 crossing of voltage VA. And we have found just few moments back that at VA equal to 0 and when dVA by dt is greater than 0, imaginary part of this line current IAL, what was that? That was IALT by root 2. So therefore, we can write B gamma AB equal to minus, it was divided by root 2. So it is minus, it is minus 1 by 3V. So root 2 भी मैं बाहर निकालूंगा, it is minus 1 by 3 root 2. So imaginary part of IAL. What is imaginary part of IAL? That is, I will write here IA by root 2. Root 2 मैंने बाहर निकाला. But condition is that VA is equal to 0 and dVA by dt is greater than 0. Okay. So your control algorithm at 0 cross at point X, that is positive 0 positive going 0 crossing of voltage VA when VA is equal to 0. It will take the sample of instantaneous value of phase A current IA. जो भी sample उसको मिलेगा यहाँ put करेगा इस equation में, plus imaginary part of AIBL. Just few moments back we proved that imaginary part of AIBL is equal to IBL T by root 2. But at positive going 0 crossing of VB, that is when VB is equal to 0 and dVB by dt is greater than 0. So therefore we will write plus, it is equal to IBL by root 2. Root 2 we have already taken out. So it is equal to IB, or you can IBL, you can say IAL, IBL. At what point? At VB equal to 0 and dVB by dt greater than 0. Okay. Then minus imaginary part of A square ICL. And just few moments back we have proved that imaginary part of A square ICL is also equal to instantaneous value of current ICL T by root 2 at positive going 0 crossing of phase C voltage. That is when phase C voltage VC is equal to 0 and it has a positive slope, that is dVC by dt is greater than 0. So I will write here minus imaginary part of A square ICL at positive going 0 crossing of phase C voltage, that is VC equal to 0. What is that value equal to? The sample, we take the sample of instantaneous value of current ICL, that is ICL by root 2. Root 2 is already taken out, so it is minus ICL. And we will write at what point? At Vc equal to 0 and dvc by dt greater than 0. That's all. Okay. So this is b gamma ab. Similarly, we can write b gamma bc is equal to minus 1 by 3 root 2. It is 3 root 2 v also. 3 root 2 v into, we have minus imaginary IAL. So minus, that is minus IAL. यही चीज मैं लिखूंगा VA equal to 0 and dVA by dt greater than 0 plus imaginary part of AIBL, that is IBL, instantaneous value of current IBL, at VB equal to 0 and dVB by dt greater than 0 plus imaginary part of A square ICL, that is ICL, at VC equal to 0 and dVC by dt greater than 0. Okay. And finally, third susceptance of the compensator B gamma CA is equal to minus 1 by 3 root 2V into पहली term में imaginary IAL itself, instantaneous value of IAL, at VA equal to 0 and dVA by dt greater than 0. Then minus imaginary part of AIBL, that is instantaneous value of current IBL, at the sample of current, instantaneous value of current IBL, when VB is equal to 0 and dVB by dt greater than 0. That means dVB by dt greater than 0 means positive going 0 crossing. dVB by dt less than 0 means negative going 0 crossing, but we have to take the sample at positive going 0 crossing. And then third term is plus imaginary part of A square ICL, that is equal to instantaneous value of current, sample of current ICL, instantaneous value, at Vc equal to 0, that is positive going 0 crossing of voltage Vc, dVc by dt greater than 0. That's all. So you have to develop a control algorithm. With the help of that control algorithm, what will you do? Your control algorithm will have zero crossing detector. As soon as your VA, phase A voltage, touches the positive going 0 crossing, it will take the sample of current IA. As soon as phase voltage VB touches the positive going 0 crossing, your control algorithm will take sample of IB. Whatever the value of IB is, that's the sample. And as soon as your phase voltage VC touches the positive going 0 crossing, that is when VC equal to 0, it will take the sample of IC and substitute in these three equations, here, here, here. So that will give you B gamma AB, B gamma BC, and B gamma CA, the three susceptances. And then put those susceptances across your load. So it will result in load compensation, complete load compensation. It will balance all the load currents. It will balance the load currents so that line currents are now equal, they are balanced. And simultaneously, it will ensure unity power factor at the source. That means whatever is the reactive power requirement of your load, that will be supplied by the compensator itself. So compensator, whose susceptances are B gamma AB, B gamma BC, and B gamma CA as calculated by these equations, it will compensate the load unbalance as well as reactive power, making power factor, source power factor equal to unity. This is how we do it, by sampling method. Why is it called sampling method? Because at positive going 0 crossings of voltages VA, VB, and VC, the algorithm takes samples of the current IAL, IBL, ICL, puts them in these equations and calculates these susceptances. And then adjusts the shunt compensator susceptances as per the calculated values for load compensation, for compensating the load unbalance and for compensating the reactive power, making source power factor equal to unity. I hope you have understood this. So this is one method of doing it. Another method, so in this case, you don't have to find real component, you don't have to find reactive component. Just put a zero crossing detector in your circuit. As soon as voltage VA touches the positive zero crossing, your algorithm will take, you will have a current sensor, and with the help of current sensor, your algorithm will take the sample of current IA. Similarly, when voltage VB touches the positive zero crossing, current sensor, with the help of current sensor, you will write a program, you will develop a control algorithm, and it will take the sample of current IB. And as soon as your voltage VC touches the positive going 0 crossing, you will take a sample with the help of current sensor. You will take a sample of current IC, put those in the equations. You will get B gamma AB, B gamma BC, B gamma CA, and therefore your control algorithm will adjust or make the shunt compensator susceptances equal to calculated susceptances for complete load compensation. This is how we can do it with the help of sampling technique. Another technique is called averaging method. Averaging method. Let us discuss this technique also. These are two very familiar or very famous methods. In this case, we express the compensator susceptances in terms of real and reactive powers. What I mean to say is, let us take B gamma AB susceptance, and we will write minus 1 by 3V into imaginary part of IAL plus imaginary part of AIBL minus imaginary part of A square ICL. We already know this. So what we will do, B gamma AB, we will divide it by V. So it will go minus 1 by 3. V into V is V square. And we will multiply it by V also. V into imaginary part of IAL plus V into imaginary part of AIBL minus V into imaginary part of A square ICL. Because if you have divided by V, you have to multiply by V also. So that is equal to minus 1 by 3V square times imaginary part. Let me take this V inside. So this will be V into IAL plus imaginary part V inside V into AIBL minus imaginary part V A square ICL. Okay. Now we know that we can now write, we know imaginary part of V into I, these vectors can be also represented as imaginary part V complex conjugate into I complex conjugate. So therefore B gamma AB will be equal to minus 1 by 3V square. Use this. So you will get first term will be imaginary part of this is V into IAL, take complex conjugate, plus imaginary part of A V IBL whole complex conjugate minus imaginary part of A square V ICL complex conjugate. Then it can also be written as B gamma AB equal to minus 1 by 3V square into imaginary part of, this is 3V square into imaginary part of, this is V star means V complex conjugate into IAL complex conjugate. I am taking it separately. Plus imaginary part of A complex conjugate into V complex conjugate into IBL complex conjugate minus imaginary part of A square complex conjugate into V complex conjugate into ICL complex conjugate. Okay. Now what will be this equal to? If you see this, B gamma AB will be equal to minus 1 by 3V square, then imaginary part of VA V IAL plus imaginary part of this A complex conjugate into V, it will be A square complex conjugate V IBL complex conjugate minus imaginary part इसका complex conjugate A आएगा, then this is V complex conjugate into ICL complex conjugate. Now what is V? What is your VA complex conjugate? That is equal to V complex conjugate, that is equal to V. What is A square V? What is A square V? A square V is VB. And what is AV? That is VC. So using this relation, B gamma AB can be written as minus 1 by 3V square into imaginary part. V star is V itself, or that is equal to VA. So we will write VA into IAL plus imaginary part. What is A square V? A square V is VB. I will write VB IBL. Okay. And minus imaginary part of AV is VC. VC ICL. Okay. This is B gamma AB. Similarly, we can write B gamma BC can be written as minus 1 by 3V square into minus imaginary part of VA IAL plus imaginary part of VB IBL plus imaginary part of VC ICL complex conjugate. And B gamma CA is equal to 1 by 3V square into imaginary part of VA IAL. उसमें बीच वाली टर्म में माइनस आता है, माइनस इमेजिनरी पार्ट ऑफ VB IBL plus imaginary part of VC ICL. Okay. Now further simplification can be done. We can write now. We can write that as far as this imaginary part of VA into IA is concerned, IAL is concerned, it can be written as average value of 1 by integral 0 to t V instantaneous value VAT at an angle of minus pi by 2 into IAT dt. So VA into IA, what is actually VA into IA? It is the apparent power. And how do you write apparent power? It is, it is the average power. And average power is, how do you write average power? 1 by t integral 0 to t voltage into current. But as far as VA star is concerned, it is VAT at an angle of minus pi by 2. Okay. So VAT at an angle of minus pi by 2 represents the voltage VAT shifted by minus pi by 2. Okay, radians in time domain. So for similarly, imaginary part of VB IBL can also be written as 1 by t integral 0 to t VBT at an angle of minus pi by 2 into IBT dt, and imaginary part of BC ICL is equal to 1 by t integral 0 to t VCT at an angle of minus pi by 2 into ICT, instantaneous value of current, dt. Okay. Now, as the relationship between phase and line quantities, that is VAT at an angle of minus pi by 2, if you represent it in terms of line voltage, it will be equal to VBC line voltage by root 3. You draw the phasor diagram, and from the phasor diagram of three-phase system, line voltages as well as phase voltages, when you draw, you will see that phase voltage VAT at an angle of minus pi by 2 will be equal to line voltage VBC by root 3. Similarly, phase voltage VBT at an angle of minus pi by 2 will be equal to line voltage VCA by root 3. And phase voltage VCT at an angle of minus pi by 2 will be equal to line voltage VAB divided by root 3. Substituting in these three equations, what you will get when you substitute in these equations, therefore, imaginary part of VA into IAL is equal to 1 by T integral 0 to T. VAT, अभी थोड़ी देर पहले, VAT is the VAT at an angle of minus pi by 2 is your line quantity, and it is equal, it's the phase voltage, it's equal to line voltage VBC T into IAT dt. Similarly, second term, second equation, imaginary part VB into IBL is equal to 1 by T integral 0 to T. What is VBT? VBT is the phase voltage. VBT at an angle of minus pi by 2. In terms of line voltage, it is equal to VCA T multiplied by line current IBT, instantaneous value of line current IBT dt. And third equation is imaginary part of VC into ICL is equal to 1 by T integral 0 to T. This is the phase voltage VCT at an angle of minus pi by 2 shifted by minus pi by 2 radians. In terms of line quantities, it is equal to line voltage VAB T into ICT dt. So we got the three equations. So therefore, what is our B gamma AB? Just few moments back we had written B gamma AB. What was B gamma AB equal to? B gamma AB was equal to 1 by 3V square. It was equal to 1 by 3V square into imaginary part of VA into IAL plus imaginary part of VB into IBL minus imaginary part of VC into ICL. ये तो अभी थोड़ी देर पहले हमने निकाली रिलेशन. And therefore B gamma AB is equal to 1 by 3V square. What is VA into IAL? It is 1 by T integral VBC IA dt. इसमें T भी है, तो T भी मैं बाहर ही निकालूंगा. So it will be 1 by 3, actually it is 1 by 3 root 2. I'm sorry, it is 3 root 2. Is 3 root 2? No. This is root 2 here, root 2 here, root 2 here. Here it was actually VBC by root 2, VCA by root 2, VAB by root 2. वो root 2 बाहर निकालो. So यहाँ आएगा, here it is 1 by 3V square. इसमें what is VA? Imaginary VA IA, that is 1 by root 2 T, है ना? और root 2 और T भी अगर आप बाहर निकालोगे, so this will be 3 root 3 V square T into 1 by T. Then integral 0 to T. पहली term है ये, imaginary VA IAL. What is that equal to? That is equal to VBC into IAL plus imaginary part VB IB, that is VCA IB minus imaginary part of VCIC minus VAB IC L dt. तो ये आपका B gamma AB बन गया. So once you have got B gamma AB, therefore B gamma BC we can find 1 by 3 root 3 V square into 1 by T integral 0 to T. इसमें पहली term minus आएगी, minus VBC IAL plus VCA IBL plus VAB ICL dt. Okay, and finally last equation, B gamma CA, compensator susceptance B gamma CA, 1 by 3 root 2 V square into 1 by T integral 0 to T. पहली term positive है VBC IAL, इसमें दूसरी term negative है VCA IBL plus third term is VAB ICL dt. That's all. So whatever control algorithm will do, it will you will have voltage sensors. You will have 3 voltage sensors which will sense the voltages line voltages VAB, VBC, VCA, and you will have three current sensors which will sense three phase currents or three line currents, IL, IBL, ICL. What your control algorithm will do, it will when it measures or senses, for example, line voltage VBC, and it also senses with the help of current sensor line current IL, it will find the product of the two. Similarly, plus this into this, minus this into this, और इस सब का average लेगा. और उस what is average? 1 by t integral 0 t. So एक cycle, in one cycle, it will take one cycle of this, and it will take average of this whole thing and multiply that by 1 by 3 root 3 v square. तो वो आपको b gamma ab देगा एक cycle में. Next cycle में it will repeat, because it is possible that in next cycle your voltage may have changed. So next cycle में it will repeat and it will keep on in every cycle. So that means 1 by t integral 0 to t पहला cycle है, दूसरा cycle है 1 by t integral 0 to t plus t1. इसमें भी यही average value find करेगा and it will find b gamma ab. Similarly, it will find b gamma bc, it will find b gamma ca. So it will take the product of these quantities, take the average value in successive cycles, multiply that by 1 by 3 root 3 v square. So that will give you three susceptances, b gamma ab, b gamma bc, b gamma ca. So you have to design your control algorithm in such a way that it is done like this, and hence you get the actual values of what should be the compensator branch susceptances b gamma ab, what should be b gamma bc, what should be b gamma ca, so that complete load compensation in terms of load unbalancing, load balancing, and reactive power compensation is done, so that you get complete balanced line currents IAL, IBL, ICL, and you get unity power factor at the source. So since it takes the average of this whole thing, that's why this method is called averaging method. So this is how, if I summarize, when we tried to find a generalized approach for load compensation, we took a delta connected load. We found the three line currents IA, IB, IC, or IAL, IBL, ICL in terms of admittances. Then we expressed those line currents in terms of sequence component of currents or symmetrical component of currents. We found positive sequence component of current I1L of load and negative sequence component of load current I2L. And then we connected the compensators across each branch of the load in such a way that they also produce the positive sequence and negative sequence component of currents, which are equal to positive and negative sequence component of load currents. And then we set the objectives. The first objective was that I2L should be equal to minus I2 gamma. That is, whatever is the negative sequence component of current required by the load because of unbalancing, that should be supplied by the compensator. And second objective was set, say for power factor improvement, we assumed some value of beta power factor angle. Say for example, for unity power factor, beta was set equal to 0, and then we, after many mathematical manipulations, we got the mathematical expressions for b gamma ab, b gamma bc, b gamma ca. But those initial expressions were in terms of sequence or symmetrical component of currents, and since it is very difficult to measure the symmetrical component of currents, positive and negative sequence component of currents, what we did, we expressed those sequence currents in terms of actual load currents. And after expressing them in actual load currents, we got three equations. First equation was b gamma ab is equal to minus 1 by 3v imaginary part of IAL plus imaginary part of AIBL minus imaginary part of A square ICL. B gamma BC was minus 1 by 3v times minus imaginary part of IAL plus imaginary part of AIBL plus imaginary part of A square ICL. And B gamma CA in terms of load currents was minus 1 by 3v times imaginary part of IAL minus imaginary part of AIBL plus imaginary part of A square ICL. So we got these susceptances of compensator in terms of load currents, but imaginary part. Then we use two methods. One is the sampling method, another is the averaging method. The purpose was to actually implement these algorithms and calculate these compensator branch susceptances in real time. Okay, so in sampling method, what we did, we found the algorithm is that at positive going zero crossing of voltages VA, VB and VC, take the samples of line currents IAL, IBL, ICL and substitute them in equations, the equations which we have written few moments back, that those will give you very easily B gamma AB, B gamma BC, B gamma CA for load compensation. In averaging method, what we do, we take, finally, this is the equations we got in the averaging method after, using the technique. The line voltages have to be sensed, line currents have to be sensed, and there, you have to take product of these currents and voltages in all the three equations and take their average. Multiply that average value by 1 by 3 root 3 V square, 1 by 3 root 2 V square, not 3 root 3 V, 3 root 2 V square, and that will give you compensator branch susceptances B gamma AB, B gamma BC, B gamma CA. This is how we actually do it when you implement these control algorithms. And you then connect these passives, and if it is a like inductances and capacitances across the load, these are shunt compensators. And if it's a closed loop system, then if the parameters, load current parameters or source voltage parameters change, it automatically calculates the new values of these compensator branch compensator susceptances, and it adjusts the capacitance and inductance values if it's a closed loop system, so that perfect load compensation is done. So this is how it is done using sampling method and averaging method. I will end my today's lecture here. I know it's a bit conceptual in nature, but it is very interesting. This is how passive compensators are practically implemented using sampling method and using averaging method. More on it inshallah in next lecture. All the best to all of you. Thank you.